And yes, thank you for having me. And I'd like to share more information about how you can actually quantify the likelihood of a failure event just from dissolved gas analysis. I'm sure you've had cases where you have a large fleet of transformers and they're given a straightforward categorization of 1, 2, 3, green, yellow, red. But if you have a handful or even perhaps unfortunately a larger number of reds or yellows, where do you start? And what we're talking about here today is how you can get a more refined risk assessment that allows you to set your priorities for your maintenance crews. Now, just get back to first principles here. What's the purpose of DGA? Well, it detects and can assess changes to a transformer's condition. It's the change that's being assessed. DGA cannot assess the condition of a transformer. So what basically happens is DGA will basically put up a flag, and if you want to understand the transformer better, you go and do follow-on testing. That's an important thing to remember. A lot of people lose sight of that. But if we can get a closer or better understanding of the dissolved gases, and particularly the energy that went into creating them, we can actually assess the severity of the change that's underway. Risk management is part of the day-to-day activity of utilities. You folks know this, and ISO has a standard around that. This is the illustration of their risk management process. And you can see that risk assessment is central to the risk management process. And once you understand the risk, you can assess it, you can get some sense of the severity. It makes it a lot easier to set priorities and then treat the risk according to your internal policies. IEEE and IEC provide standards for interpreting gases, as I'm sure you all know. Based on feedback from lots of transformer experts, lots of people have a lot of experience in the field. But they're limits-based methods, and they've worked for a long time in helping identify a lot of problems, but they still miss a material number of failures. And the feedback we get is that there's still an excessive number of false alarms being generated, and it is well recognized that they are not suitable for interpreting data from online DGA monitors. So all that great information, how do we get the most out of it? Okay, you can improve your reliability. You can elevate your program, avoid false alarms with the application of reliability statistics. Okay, and it also will allow you to interpret your monitor data in a meaningful way. On top of that, like I was referring to, rather than just getting green, yellow, red, you can put a quantity in terms of what the likelihood of failure is from the observed gassing. So how did we get there? So with a little bit of digging into a lot of data, and we were very fortunate to have some of our customers give us their failure data, we were able to create a failure model that looks something like this. Now you'll notice that the x-axis is not a function of time. It is a function of the fault energy, sometimes referred to as the normalized energy intensity, NEI. And what that is simply understanding that the gassing is a symptom of a problem. And if you can, you can quantify the enthalpies of formation of each of a drop of mineral oil or a molecule of mineral oil. What does it take to convert that to a molecule of each of the key gases? You can use that as a weighting to get an understanding of how much energy, approximately how much energy went into a fault. Of course, it is difficult to account for gas loss. So if you have a transformer that's leaking gas, not all of it will be accounted for, particularly when you're doing manual sampling, i.e. you have a long period between samples. It's much easier to catch those types of things with online monitoring. Now, what's the important thing in this model? Well, the standards basically imply the more gas you have, the more at risk you are. And if you notice here, is that for a transformer that's never gassed before, it indicates that the failure rate will rise very quickly, but then peak and start coming down. And this is consistent with many stories we've heard from the field from transformer experts who have had some large old transformers that may have lots of gas in them. They have a rich gassing history. My kids laugh every time I say something like that. But they have a rich gassing history, but they are quite comfortable with that, operating that transformer. They have other things that they need to do, other higher priorities. They still keep an eye on it. But this curve now represents the experiences we're hearing from all those transformer experts in the field. This is a failure model based on data, operating data, and failure data from thousands of transformers. This does not represent the behavior of any single transformer. The other notable thing that comes out of this model is where the 90th percentile lines up. Because if you recall the standards, they generally suggest as a starting point that you raise the first alarm, you raise the yellow flag when you hit the 90th percentile, i.e. the worst 10% of transformers that gas. And the red flag goes up at the 95th percentile. Well, if you notice, they occur to the right of the peak. So by the time the standards, if you follow the standards, by the time you've actually raised the yellow flag, you've already missed the most critical period of gassing and the peak of the failure rate. This would explain why there are a material number of failures that are missed by DGA. Okay, and in fact, the peak, as you can see here, occurs at about the 82nd percentile. So, should we just simply move the alarms back to raise the alarm at the 82nd percentile, or even before that? Well, I think we can do better than that. Okay, and what we do with this model is for any particular transformer of interest, which is basically every transformer when you're doing your annual sampling, you can compare it with the model. And this dotted line represents the fault energy, the current fault energy of a particular transformer of interest. And what you have under the area of the curve to the left of that is what's referred to as the cumulative severity. That indicates how many transformers that have gas would have failed before that point. Okay, so that basically tells you how lucky you've been playing Russian roulette so far. Okay, that's good, it's useful to know, but it's a rear view mirror look at your situation. And what you really want to know is what's likely to happen tomorrow. If the transformer is currently gassing, we can look at the current rate of gassing and estimate how much area under the curve will be covered over the next year. That's referred to as the hazard factor. And that's the quantity you can use to score your transformers and rank them for priorities for maintenance. But basically, it tells you what the likelihood of failure is over the next 12 months. This is a very useful piece of information, and it allows you to take your transformer fleet and make informed decisions about it. Yes, you can still have a basic green, yellow, and red score, but the hazard factor refines your prioritization. Okay, so that you can say, hey, this is where I really need to spend my time right now, or perhaps I just need to shut that transformer down. That, of course, is your decisions. You know, we understand what the data is telling us, but we don't understand, or we're not intimate with your fleets. But this really changes the game in terms of how you can optimize the maintenance of your transformer fleet. So seeing this in action, the data for the initial model came out from a couple of large utilities, which was not this one that's actually represented in front of you. This particular utility had a failure. They didn't catch it. It was before it was just as we were learning about reliability-based DGA, and conventional DGA did not catch it. And they asked us to double check, and sure enough, conventional DGA wouldn't have caught their particular failure. It was a catastrophic failure that had a lot of collateral damage. And they asked us to check their whole fleet. Once we raised the flag that said reliability-based DGA would have caught this one. So we looked at a population of 7,200 transformers. And interestingly, both reliability-based DGA and conventional DGA flagged about 1,700 transformers. But the interesting thing was only 731 were common, which means we had some big differences here. Those differences, the ones that conventional DGA flagged that reliability-based DGA did not, were false positives. The engineers knew those transformers. They were the transformers that had a rich gassing history. They were comfortable operating them. There weren't any real issues with them. What they were more concerned about was this group, because the one that failed was part of that group, and they started investigating. Of the first 68 units checked, 63 were confirmed to have problems. 2, there was some bad oil samples, and we had 3 false alarms. Remember, this is statistics. They'll never be perfect, but you can certainly, with a different view of the data, get a much improved interpretation and get more insight in terms of what's going on with your fleet. So what does that basically do for you? Well, DGA contributes to a predictive or a condition-based monitoring maintenance strategy. And, even though you're doing it on a scheduled basis, the whole point is you're trying to identify when conditions change so that you can go and do other investigations and maintenance. That's what the nature of a condition-based maintenance strategy is. But being able to tie your gassing behavior to transformer failures actually elevates your DGA program to a reliability-centered maintenance program, which gives you the most efficient maintenance schedule, as we just showed, and just allows you to get the most out of your fleet with the precious resources you have. This is becoming more important these days, or has been over the last 6 months or so, as the supply chain has had all those disruptions, and the lead times for power transformers has gone from 6 to 12 months up to 24 to 36 months. We're finding more and more of our customers are really paying close attention to this. The interesting thing about this technique is it works regardless of sampling frequency. It isn't, you still have to pay attention and do a bit of signal processing to monitor data, but it works very well. It doesn't raise alarms inadvertently for you, okay? And it'll give you that meaningful interpretation that is consistent with the interpretation of the lab data. As was just discussed, you're still going to do manual sampling of transformers that have monitors. You might do it less frequently, but you still want to compare, because you want to double check that the monitor is working correctly, and vice versa, as was discussed. Your monitor may actually be working very well, and you may want to validate the lab results. Both scenarios are possible, okay? And reliability-based DGA does do a full interpretation of your DGA monitor data. Okay, so you don't have to have it just sitting out there and it driving your operations center crazy with SCADA alarms. Okay. The other thing, thank you, Leon, for mentioning it, is yes, this type of analysis works for all gas combinations. We've been looking at many different combinations, typically driven by the DGA monitors that are out in the market. And even there's a good model that's even presented by just hydrogen. So those statistics can be applied across the board, and you can do a quantitative assessment based on any combination of gases. Yes, to varying effects, okay, but I think when you look at the price for something like a hydrogen monitor versus a multi-gas monitor, I think there's a lot more opportunity to deploy monitors, particularly on the mid to lower end of your power transformer fleets. I would encourage you to look at the economics of it more closely. All right. So it's really short and to the point today. You know, you look at the ISO model and you recognize that DGA itself is a three-step process that very much, it's a risk assessment tool. That's what it's here for. And if it's done right, it can be highly effective at improving the reliability of your fleet, making sure your maintenance resources are applied to the right places, and also can be applied to your online DGA monitors of all gas combinations, such that you're getting the most out of your monitors and the most out of your precious maintenance resources. Okay, and that's just myself saying the same thing over again. And if you want to dig deeper, you know, as you may have seen from our logo, we're all about the science. The papers are out there in the open. We're happy to share, and I would encourage you to dig deeper or call us if you'd like to learn more. Thank you very much, Randy. And anybody wanting to learn more, that's where you can reach us.
Great, thanks very much, Drew. Thanks very much, John. We have a couple of questions. How do we do smart analysis on the DGA online sampling data? Is there an industry standard for DGA threshold for both automatic alerting and alarming?
With online monitors?
Yeah.
No, there isn't. In fact, the standards specifically state that the C57104, for example, specifically states that this method is not appropriate for monitor data. The challenge with online monitors is, you know, to varying degrees, they're very sensitive instruments deployed in a quite a harsh environment. And we see that they will vary, the data can vary for issues unrelated to the sensor. It could be electrical issues. We see seasonal variations. All of those things need to be accounted for. And you can't just rely on simple limits-based interpretation of the data. If you set a limit, well, that might work for you in the summertime, but it'll be wrong in the winter or vice versa. And that's the challenge with that. I know that there's a new standard coming out. They're working on that with IEEE for online monitoring, but I think it's fairly generic in flavor and won't answer that specifically. So quite a bit of work has to go into processing the signal. It is a signal. You know, I have a communications background, and you know, it's just another form of a signal. And if you know what you're looking for, you can clean it up quite nicely, and then apply something like reliability-based DGA to it, as opposed to a simple limits-based solution.
What would you say the top 3 challenges are when it comes to DGA?
So DGA in general, or
yeah,
or online monitoring?
Oh, online monitoring, DGA.
Online monitoring. Okay, online monitoring is top 3. The reliability of the sensors has been a big issue. Technology is improving, but you know, it's fairly expensive. We're seeing some improvements in technology, but the simpler you can keep it, the better. So if you can, you know, if you can get away with a smaller, simpler monitor, then you might be better off from a reliability perspective. The communications.
That was the point I was going to ask next about.
Communications is really there's so many monitors we hear about out there that are actually not connected, or the communications have broken down. We work very hard to help facilitate that, but there's only so much you can do, particularly if they don't make a connection to the monitor. But communications is a big issue, and if you buy some sort of monitoring system like a central data interpretation system, it ought to also monitor the communications channel for you and raise the flag that says, hey, you got to go pay attention and get this guy reconnected again.
Is it true a large number of online DGA monitors are not connected to the transformers?
Not connected to the transformers?
Yeah.
Well, I have heard of some utilities buying them and having them in the warehouse and not getting them.
Well, I mean,
that has occurred. I think more often than not these days, though, on new transformers, utilities are speccing them in, so they're being installed at the factory. The issue is the communications more often.
Mm-hmm. Right. Okay, well, that was good questions. All right. Thank you very much. I appreciate it, John and Delta X, for making the presentation.